So on that packet from Monday that was called in class, work in, work done by friction, and intro to lack of, we had gone through and we worked through a bunch of the kind of individual problems. And I had suggested that you number these. I think I suggested you number them. Maybe I said I should have. I think I said I should have, but maybe we didn't actually ask you to. But we went through and we kind of defined a bunch of these things to kind of refresh our memory, hopefully, or to reteach whatever it may be on those types of problems. So I think we left off, I think we did this problem on the second page that says if a person does 500 joules of work in 10 seconds, how much power? Did we do that one?
Yeah.
This one?
Yeah.
Okay. Not this, okay. So I want to pick up at what I'm going to call number 16. So when we look at number 16, it's a couple different, well, I guess let me take a step back. When we talk about work, because that's what this question, if a person applies a force of 10 newtons to push an object 13 meters along a frictionless surface in 15 seconds, how much power do they have? Part of the power calculation is we have to determine work. And there's two different equations that we can use to calculate work. And I will show you those two equations here in a moment. So in order to calculate work, there are two formulas that we could use. The one formula is on that green sheet. I think it's the second equation down under the energy. It says work in is equal to plus or minus our applied force times displacement. Okay? From there, we can solve for work in. In this problem that we're about to do, that's the way we're going to go. But the other way we could solve for work in is we could use that equation as well. And we could solve for work in there. This is a two-location problem. We're looking for V1s, we're looking for V2s, we're looking for H1s, we're looking for H2s, we're looking for spring stuff at the two different locations. So there's really, like, again, the two formulas are either work in and apply force, or when you compare two locations. So depending upon the information given, depends upon kind of the process you want to go with. This particular question says, if a person applies a force of 10 newtons to push an object 13 meters along a frictionless surface in 15 seconds, how much power do they use? Box, surface, applied force, 10 newtons, displacement, 13 meters. They're pushing it, which causes it to move. So if it's pushing it to the right, you're moving it to the right. And the idea is how much power is it going to have? Because there's a time of what, 15 seconds, I think it was. But our equation for power is work divided by time. So the first thing we got to do is we got to solve for that. That's the idea. So this work, or this is the other equation we could use to solve for work. Given the fact that there is an applied force and a displacement, this is the one we want. Okay, so my work in is equal to plus or minus, I'm going to skip that for a moment, of 10 times 13. Okay, now we have to make the choice about whether, and I'm going to erase this in a second, if it's the plus or if it's the minus. And if you don't remember which one it is, or how do you determine that, it's the directions that the objects are going. Are they in the same directions, or are they in opposite directions? If they're in the same directions, it's the third question on the first page. Then that's an example of the same. The fourth question on the first page was the opposites. Okay, so in this situation, they're in the same. And if they're in the same direction, is it the plus or is it the minus?
Plus.
It's the plus. So my work in is equal to plus 10 times 130, or it's going to be plus, 10 times 13 is going to be 130 joules. My work in is going to be 130 joules. Now, once we know work in, we can go and use this to determine my power. My power equation that I have down here is work divided by time. So our power is equal to the work divided by the time of 8.67 watts. In order to calculate power, we need to know time. Time could be given, or I could be not so kind, and I might say you got to calculate it. And the way you'd have to calculate it is fast. Initial velocity, final velocity, acceleration, displacement, could then determine. There's not enough information in this problem to do that, and I don't need to because I give you the time of 15 seconds. Questions on that? Two ways we can find work in. You could use applied force, or you could do it as a two-location problem. With V1s, V2s, H1s, H2s, spring stuff at location 1, location 2. Which is how, when we do our stair lab or our power lab today, we will calculate work in by two locations. We start on the bottom of the steps, and we then climb to the top. Just like Matthias, my buddy, did in that stair climb at the Willis Tower. So then we could say, hey, at location 1, what's my velocity, what's my height? At location 2, what's my velocity, what's my height? Then plug into that. Number 17 is really went for the sole purpose of review. And it's a force problem and a force problem only, but I put it there just to kind of hopefully refresh our memories slightly. And I'm gonna go fairly quickly, so if there's a question, please ask. Otherwise, I'm just gonna kind of go with the good kind of mentality. So, it says a 10 kilogram object is sliding along a surface has a coefficient of friction of 0.3. It's got a coefficient of friction, which is mu, and my mu has a value of 0.2. What is my force of friction? So let's just pretend that the object is moving to the right. It doesn't say, but let's just pretend. If my object is going to the right, which direction is my force of friction going to be? Always opposes, so it's going to be going to the left. And I'm trying to figure out what that is. So if we look at that forces section on our note sheet, there's two ways we could find friction. Newton's second law, or force of friction is equal to mu times our normal force. I was looking to see if there were any Foster transfers here. If you had, maybe people on video had Foster, he just calls it N instead of F of N, but that's a slight difference. Also, when we talk about other forces, I call it force of gravity, and I know Foster just called it mg. So slight differences, but really kind of all the same ideas. So there are the other forces that are acting on this. It doesn't talk about applied force. I don't really care if there is, but there's no mention about being pulled or pushed or anything. He just says it's applied. And you can say, well, why do I need to know that? Well, the reason we need to know that is because we need to know our normal force. And if you recall, there's no magic formula for normal force. It's kind of by a process of elimination of, are my forces in the y direction balanced or not? And if they are, all of my ups minus all of my downs have to add up to 0. And if this object is sliding this way, they will be balanced, which means these two are going to be the same. So how do we determine what these are? Well, F of G is M times G, and 10 kilograms is my M. So our F of G is equal to 98 newtons. This is 98 newtons. We good so far? My forces are balanced in the y direction. This object doesn't accelerate off the table or through this table. Therefore, my forces are balanced, which means then this is also going to be 98 newtons. My ups minus my downs had to add up to 0. Now, once we know that, I can say 98 times U of 0.3 is equal to that force of friction. So my force of friction is 29.4 newtons. How's that? You still okay with some of that stuff? I know forces wasn't our best unit. It's like I mentioned at the beginning, it's going to be the hardest probably of the entire year. And for some of you, you did really well, and some of you struggled more. So there is a little bit of that. That's the parts that I'm expecting you to still be able to do. So if there aren't any questions, I'm going to say we're okay with that. We're moving forward. Okay. So that's really the purpose of number 17, was just to kind of say, hey, remember there was something that we did there. Where's my buddy Matthias? Matthias, where are you, Matthias? Oh. Got him. Got him tied. All right, so in interest of time, I'm going to talk about a lot of kind of general what we would do's with these next couple problems, and not really, I'm going to do one, my plan is to do like one more calculation with you, which tends to be a pretty kind of putting all of the pieces together type of one, but I'm going to talk about those first two questions on page 3. Okay, so on page 3 of that packet that we got on Monday or Tuesday, I'm going to look at that first one, which numbered wise, I don't even know what number that'd be. 16, 17? 18. It says a 10 kilogram object slides along a surface that has a force of friction of 25. How much work does friction do? There's two ways, just like there's two ways we can solve for work in, there's two ways we can solve for the work done by friction. The work done by friction, there's a formula that is equal to the opposite of our force of friction times the displacement. If you know work in, if you know force of friction and the displacement, this would be the one you want. In this problem, I tell you the force of friction is 25, and the displacement is 14. I'd be plugging in numbers. Force of friction is 25, displacement is 14. There's an opposite there, so whatever that number is going to be a minus. It's removing energy from the system. That's one way we could calculate the work done by friction, which is what that one would have been. The other way we could solve for work done by friction is we could solve for work done by friction in that equation as well, where we'd be comparing two locations. You'd be looking for V1s and V2s, H1s and H2s, spring stuff and spring stuff. And you might be able to solve for it there. So it really kind of depends upon the situation that you're given. In that particular problem, I point blank gave you the force of friction. That was 18. In 19, not going to do it either, just in terms of interest of time, I'm going to talk about it. 7.5 kilogram object slides along a 13.5 meter long surface with a coefficient of friction of 0.2. How much work does friction do? And how much work does friction do? One of these two is the way we're going to approach that. This problem is also going to be using this one. It's just a couple steps first. Is you have to calculate that force of friction using the coefficient times the normal force. And before you have to recognize that your forces in the y directions are balanced, therefore your normal force and gravitational force are the same, therefore, then, there's maybe two therefores. Okay, it's another equation using coefficient of friction and force of friction to kind of go through and solve for something. But if you guys are okay with it, I'm not gonna do that calculation either. But you take mu times the normal force, that gives you the force of friction, and times your displacement. Okay with that? Okay, we are gonna do this next one, and the reason why we're gonna do this next one, it's a lot of moving parts. It's a lot of different steps to kind of put it all together. So it's kind of putting, it's about as many pieces as possible that you can do. I guess the one thing I could do to make it more is say how much power, which I don't directly ask for power, but I suppose I could. I guess that'd be number 20. We have a 25 kilogram object that starts from rest. V1 is equal to 0, I don't like it right there, I'm gonna move that. V1 is equal to 0 meters per second. I'm telling you it starts at rest. V1 is equal to 0. A 25 kilogram object starts at rest and is pushed across a level surface that is 10 meters long with a force of 80 newtons. It's being pushed, that's an applied force of 80 newtons, and it's being pushed 10 meters. And I hope it's implied well enough that if I'm gonna push an object, it means it's gonna move in the same direction that I'm pushing it. So it's gonna be moving to the right. If my applied force is to the right, its displacement is gonna be to the right. If the coefficient of friction is 0.3, so mu is equal to 0.3, which then automatically tells us there is a force of friction. Right? Mu means there's going to be a force of friction. How much work is put into the system? Work in. How much work does friction do? Work done by friction. And then what is the final velocity? And really there's three different steps that kind of get me to the ultimate question of what's our V2? And the way we're going to solve for that V2, just to kind of give you some foreshadowing, and well, actually it's not foreshadowing if I point blank tell you, is we're going to have to use this equation. We will eventually use this equation to solve for V2 in KE2 that was within ME2. That's ultimately what we're going to do. So why were those first two steps there? Those first two questions, I should say, is very direct to say, solve for that first, then solve for that, then plug it in and use this equation. That's why those kind of intermediate steps are there. I'm going to leave my free body diagram for a moment. There are other forces, right? There is a F of G, there is an F of N. We'll come back to those if we need them. We're gonna, but if we need them, we'll come back to them. So the first question being asked is, what is our work in? Okay, that's the first kind of prompt or the step that I'm asking you to kind of calculate. So there's two ways we could do it. We could use this equation, or we could use this equation. This one isn't the one we're gonna want because we don't know V2, we don't know all that information. We don't know work done by friction yet. So we're gonna use that one. We're gonna use this one. So work in is equal to plus or minus the applied force times our displacement. So work in is equal to plus or minus. Now let's talk quick. Is it the plus or is it the minus? Why? Same direction, good. Because it's in the same direction as the displacement, plus. And then we're simply plugging in 80 for the force, 10 for the displacement, work in, is equal to positive 800 joules of work. Those 800 joules of work are probably going to give this object more speed, right? More kinetic energy. Because if I push something, it's gonna speed it up. So that was the first question that was asked, and the reason is we're gonna use that there. Okay, it's kind of stepping into that piece. The next question that's asked is, what's the work done by friction? Our equation for that is either this, which we have enough information, or the work done by friction equation, which is on the green sheet. Third one down, I believe it is in the energy section, minus force of friction times displacement. The issue is we don't know that number yet. And in order to know that number, F of F is equal to mu times our normal force. We have to figure out our normal force. And how do we know what our normal force is? We have to then figure out our F of G first, right? So, do you want me to write out F of G is equal to M times G times 25 times, okay. Then if we're okay with that, M is 25, G is 9.8. So when you multiply those two numbers together, we get 245 newtons. The F of G of this object is 245. Third equation down in the force. Second equation down in the forces section on the green sheet. M times G, 245. What's true about these two forces? Because it's not accelerating, my forces are balanced, so this is 245 newtons as well. Then we can plug that number into this equation. Coefficient of friction is mu, 0.3 times 245. Our force of friction is 73.5 newtons. Now we can come over here and we can say, what's our work done by friction? Well, our work done by friction is the opposite of 73.5 times 10. Always opposes, that's why it's always going to be, oops, there's an equal sign right there, equals. Our work done by friction is then going to be negative 735 joules. So now that we know this, and we know this, we can use those in here. Okay, so again, V1 starts at rest. The final question is, how fast is that object going? Now in the past, we could have done a Newton's second law, mass times acceleration, add my right, subtract my left, determine A, then do a Fab 5. This is a different approach to it. So now what we can do is, using this equation, work in plus the work done by friction is equal to change in mechanical energy, which change in mechanical energy is ME2, my final mechanical energy, minus my mechanical energy at location 1. And I'm going to expand that out, work in, before I plug in any numbers, is equal to ME2, KE2, PEG, 2, PEE. 2. That's ME2. Minus ME1, KE1 plus PEG1 plus PEE1. Can we still see this in the screen? No, just barely, but okay. Thank you. So this is our fully expanded equation. Let's cancel a lot of stuff. So at location 2, we're comparing 2 locations. We're looking for a V2. Okay, it's a level surface, okay? And then there's no springs, right? So we're trying to solve for V2. Gotta keep that one. Oh, I'm sorry, let's start here. Is there a work in?
Yeah.
Right, we already calculated that. There's implied force and displacement, yeah. Is there work done by friction?
Yeah.
Yeah, we already calculated that, negative 735. Okay, now energies. Is it moving at location 2?
Yeah.
Yeah, we just don't know how fast.
No.
Location 1 compared to location 2, are my heights any different?
No.
So then let's define H2 to be,
0.
and H1 also to be,
0.
okay? So we can cancel out my heights, right? Level surface. Springs anywhere?
No.
No springs mentioned anywhere across both of those out. Last thing we gotta look at, KE1, is it moving at location 1?
No.
Because it says it starts from,
Rest.
absolutely. One more, kind of breaking this piece down before I plug in numbers. Work in plus work done by friction is equal to, okay, just kind of, now KE is 1/2 mv2 squared. Now I'm gonna plug in numbers. Green. Work in, we've already calculated work in to be 800, positive 800 at that. Work done by friction, negative. So it's plus, but it's gonna be plus that negative. So it's gonna be minus 735, which is equal to 1/2 the mass, 25 times V2 squared. This is gonna be a positive 65. The difference between those two, 800 minus 735, is equal to 1/2 of 25 is 12.5 V2 squared. Divide both sides by 12.5, and we get, divide by 12.5, divide by 12.5, we get 5.2 is equal to V2 squared. I'm breaking my pattern because I don't know, I'm not really concerned anymore about it. Okay, but that's not my final answer. We need to take the square root, take the square root, take the square root. We get a total of final answer of V2 of 2.28 meters per second. Okay. Now, the only thing that would be more challenging for you, for me to ask you would be then now is how much power? And then you'd have to do a Fab 5 because now you know initial velocity, you now know final velocity, you know displacement. You could, in sense, then determine time, could, Fab 5, and then power would be your work in divided by that time. That's not what this problem's asking. I'm not gonna do it, but technically we could. That was a lot. I know there's a lot of steps there, but I wanted to kind of I wanted to get through that problem. Before we kind of move on to that last piece. Anything, I kind of went fast. I kind of hopefully assumed that we remembered some of that forces stuff. Is there any questions that I can clarify? All right, in a moment, well, I shouldn't say in a moment, in about 3 moments, whatever, I don't know what a moment is. In a little bit, we're gonna do our own stair climb similar to the Matthias calculation we did. Okay, just keep in mind that this calculation, we made the same assumption that we're gonna assume that you start on the bottom at rest and you end at the top at rest. You typically are gonna define the bottom of our staircase to be 0 because we're gonna climb to the top of the staircase. We're gonna measure a step and all that stuff. I wanna talk briefly, I'm gonna try to keep it brief, but You guys know me, I'm never that brief. About the homework sheet that I gave you for tomorrow. So work and power practice is called. These are going through and doing a series of calculations that are I'm trying to kind of break them into pieces. So in this first one, an alien does 600 joules of work. I'm telling you the work in. Okay, in this equation, I'm telling you the work in, if you needed it. If we're using this equation, I'm telling you this number. Okay, question A is what force does the alien exert? I'm telling you the work. I'm asking for the force. If we only knew his displacement, we could then calculate that, which we do. Okay, so this is saying, this is my work in, what's my applied force? This becomes a two-location problem. Work in plus work done by friction is equal to ME2 minus ME1. It talks about it being frictionless. So work done by friction, cross that thing off, right? Talks about being a frictionless surface. Let's assume it's flat, so no changes in heights. It's very similar to that ME1 equals ME2 in terms of a lot of the stuff we cancel out. Probably going to be the same too. We're solving for V2. Okay, what is the velocity after 4 meters? That's our displacement. How long? This is a Fab 5. There's no way to get around it. This is a Fab 5. You now know V2, you know V1, you know delta X. You can solve for time. Once you know time, power, work divided by time. Work divided by time will give us power. All right, trying to keep moving here. Number 2 is similar, except for now this time I'm giving you the applied force and I'm asking for the work. Above I gave you the work and asked for applied force, so it's just doing the opposite. Two location problem, ME1 equals ME2, or work in plus work done by friction is equal to ME1, ME2 minus ME1, Fab 5 with a power calculation at the end. This problem, I think number 2 is also a frictionless surface. Once you get to problem number 3, now I give you a coefficient of friction, so that means there is going to be work done by friction, which then we address, right? What is the force of friction? What is the work done by friction? Then work in plus work done by friction is equal to. Okay. The very last problem is going to be very similar to the Matthias problem and the calculation that you're about to do on this lab. But instead of climbing a flight of stairs, we're climbing a mountain. Okay? You start on the bottom, you end at the top, you time yourself. Work in plus work done by friction is equal to our change in mechanical energy. Okay, and then there's a horsepower calculation or a conversion, and I'll talk about that when we talk about the lab. So, we are about to do this lab. This lab, just for the record, is not a practice to learn grade. This is a standard S8 labs, and it's one of a handful of labs we'll do throughout the semester, so that each one of these labs has a bigger weight bearing on your overall grade. So I encourage you to do this. We're going to go through, hopefully you can kind of read this. If not, I'm going to read it to you. Height of the stair, of a stair, is 0.167 meters. The measured a stair last hour is 0.16 meters. And there are 24 of them. Okay? So what we're going to do is we're going to start on the bottom of the staircase. You're going to go up half the flight to the landing, and then you're going to keep going to the top. We're going to make the same assumptions that we did with Matthias, as you are just as world-class athlete in my mind as he is, that you don't want to cheat, do what's right, care for everyone, embrace excellence, DCE, right? V1 is 0, V2 is 0, H1 is 0, that's your H2, whatever these two numbers are, right? 24 steps at each one is 0.16, that's your H2. Then you're going to calculate your work in, and the way we're going to calculate the work in is work in plus work done by friction is equal ME2 minus ME1. Okay, it's going to be that problem. But in that equation, you're going to have to do a PEG, which is going to be M times G times H. So you need to know your mass. That's what this is asking you for right here, is your weight in pounds is going to need to be converted into kilograms. And I'm going to say this, it does say, show me the conversions. I don't really care about the weight conversion. And if you are sensitive about your weight, and you want to lie about your weight, I won't know and I don't care. You just need to have a mass. Okay? The way you do convert that, though, is if you were 200 pounds, it's like chemistry, stoichiometry, unit conversion, dimensional analysis, whatever you want to call it. You start with however many pounds you are, and 1 kilogram is 2.2 pounds, so we would divide by 2.2. Okay, you need a mass in kilograms, not in pounds. Okay, so you're going to need that because m times g times h, you need it in kilograms. So then what you're going to do is once you determine that, your total height, solve for work in. It's going to be in the thousands. It's going to be in the thousands. Okay, doesn't matter how fast you go up the stairs. It's based upon your height and your mass. That's it. Okay, depending on how much you weigh, depends upon how much work it is, but it's going to be in the thousands. The amount of time it takes you is really up to you and the effort you put forth here. I have two rules of this. Rule number one is you got to at least walk up at a normal pace. You can't do like, let's see how slow I can just walk up normal. If you want to run, great, go ahead. I don't care. That's rule number one, is you got to at least walk at a normal pace. Rule number two is you aren't allowed to trip and smash your teeth on the stairs because I don't want to deal with that. Okay, so no tripping and smashing your face on the stairs. Okay, as long as we do those, we'll be fine. So you are going to have to time yourself. Take your stopwatch, take your stopwatch. You guys all carry stopwatches. Separate stopwatches, like the sole purpose is the stopwatch, right? Phones, iPads, whatever, right? You're going to time it. Then you're going to calculate your power. Once you determine this, take work divided by time will give you your power. That's going to be in the hundreds. It'll be a couple hundred. If you run, it's going to be less. If you weigh more, it's going to be bigger. Wait, I'm sorry. If you run, it's going to be bigger. If you weigh more, it's going to be bigger. And then there is one last conversion. So once you determine how many watts of power you produce, I'm going to ask you to convert that to horsepower, which is going to be however many watts you have divided by 745.7 will give you horsepower. Most of you are going to be like a third of a horsepower. Every now and then I do get a few students who run, they're heavier, they get like horsepower. Okay, it is possible, but just kind of realize that. So that's the idea. The data collection is really quick. Most kids took like about 15 seconds to get this flight to the top of the stairs. So it's not going to take very long. The only thing you really need to take with you, we're just going to go that staircase right over there, is something to time with. We're going to go there, we're going to walk there, you're going to time yourself up, and you're going to come back down, stay out of the way of others. I'd say let's go up on the inside, on the left-hand side, and then come down on the right-hand side. Give some people some space. If you want to run. But then go up, come down, and you're going to come back. Now, when you come back, it's going to be close to leaving. A lot of students last hour stayed right up until the end. They finished this lab, they submitted, and they were done. It's a pretty quick calculation. Or they said, hey, I don't understand this. Can you help me with this calculation? Absolutely. It is a work in plus work done by friction is equal to change in mechanical energy problem, though. But it's a little bit different than the one we did because now we're looking for PEG, not KE, just to be clear.